Hi everyone, I'm Jinzhao from Yale. Today I will talk about our work on the optimal fixed price mechanism in bilateral trade. This is a joint work with my advisor Yang Cai. Let us first introduce our setting. The problem we consider is bilateral trade, which is a quite fundamental topic in economics and is pretty simple. There is only one item to sell, and there is one seller and one buyer. The seller currently holds the item, and she has a private cost S, maybe for producing this item, and the cost is drawn from distribution Fs. The buyer has a value B for getting this item, and also B is drawn from a distribution FB. And here, Fs and Fb are independent. Our goal is to design an efficient mechanism to trade this item between the seller and the buyer, and we will define what is efficient in the following. Moreover, we wish this mechanism satisfies three basic properties. The first one is ex post IR, which means that participating in the mechanism will never be a bad choice. The second one is de-seek, meaning that truth-telling is always the optimal choice in any situation. The third one is budget balanced, which means that the mechanism itself does not earn or lose money from the trade. For example, suppose here the seller wants to sell a pineapple to the buyer. Suppose the cost for the seller is deterministically 5 and the buyer values the pineapple deterministically at a price of $10. Then, a possible mechanism may operate as follows. It first asks the seller, are you willing to sell the item at a price of $7? The seller will say yes because the price is higher than her cost. The mechanism will then come to ask the buyer, would you buy the item if the price is $7? The buyer will also say yes because her values for this item is higher than $7. Then the mechanism would just let the buyer buy this item from the seller at a price of $7 and the trade happens. If we generalize such idea, we can get a family of mechanisms called fixed price mechanism. The mechanism first announces a price P, which could possibly be random and depends on the seller's and also buyer's distribution. And then the mechanism would collect the cost S from the seller and also the value B from the buyer. Then the trade happens if and only if the seller is willing to sell her item at a price of P and the buyer is willing to buy the item at a price of P, which means that S is at most P and B is at least P. We could see that this fixed price mechanism satisfies all the three desired properties that we stated before, since like for the seller or the buyer, the mechanism is actually a positive price mechanism, so it satisfies IR and de-seek. And also this mechanism only suggests a trade at a price of P, so it's also budget balanced. Surprisingly, Hegarty and Rogerson proves that the other direction also holds. Namely, any mechanism satisfies IR, de-seek, and budget balanced must be a fixed price mechanism. Therefore, this means that we only need to focus on fixed price mechanisms in this talk. As we stated before, our goal is to find an efficient mechanism while satisfying the three properties. The most ideal case is that do we have mechanisms that trade efficiently, which means that the mechanism will let the trade happen whenever the value of the buyer is higher than the cost of the seller? Unfortunately, Meyerson and Satterthwaite proves in 1983 that this mechanism does not exist. Therefore, it is natural to ask that if there has approximately efficient trade. So in this paper, we consider approximation in social welfare. We could see that in the efficient trade, we could always allocate the item to the agent with the highest value. So the optimal welfare is the expectation of max S and B, so it is our benchmark. For the welfare of fixed price mechanism, we could see that in the beginning, the seller holds the item and the trade happens if and only if S is at most P and B is at least P. So the social welfare for any fixed price mechanism is this term. And our goal is to design a fixed price mechanism that maximizes the approximation ratio in social welfare. So our paper considers how to design approximately efficient mechanisms under different information settings. We first consider the most classic setting, where the fixed price mechanism has full prior information of the buyer and the seller. Namely, the mechanism has full access to FS and FB and can choose its price according to them. This is the most standard setting, and there has been a rich series of results in this setting. In this setting, Dobzhinsky and Blom-Rosen provides a 1-1/E approximate mechanism using seller's quantile information, and Kang, Pernis, and Wondrak recently improved the approximation ratio slightly with a small constant, which is roughly 10 to the -4. So for our paper, we characterize the approximation ratio of the optimal mechanism in this setting by two families of factor revealing programs. So one lower bounds the optimal ratio and the other one upper bounds the ratio. What's more, our factor revealing program can be arbitrarily close to the optimal ratio as the size of the program grows. Then we choose two sets of specific parameters and solve the programs numerically, and show that the optimal approximation ratio, we call it R star, is at least 0.72 and is at most 0.7381. We also have a simple fixed price mechanism that corresponds to the lower bound of 0.72 and a hard instance that provides the upper bound. We could also see that, like our result, significantly improves the approximation ratio. So we next consider the setting where we only have one-sided prior information. So this means that we only know the distribution of the seller or the buyer. So in this setting, Kang, Pernis, and Wondrak shows that if the mechanism only uses the quantile information from the seller, then it is impossible to beat 1-1/E. But surprisingly, we find that if we do more than only using the quantile information, it will be much better. We prove that the optimal approximation ratio, only knowing the distribution of the seller or the buyer, is exactly the same as knowing both of them. So this means that if we already have the knowledge of one distribution, knowing the other one does not really help in the worst case. And this is our second result. So we also consider a more limited setting where the mechanism only knows the mean of the seller or the buyer. So this means that the mechanism only knows one number. So that is the mean of the buyer or the seller. So one does not expect that fixed price mechanism could have a good performance in such minimal information setting. But it is really interesting that we find the optimal mechanism in such setting, and the optimal mechanism is quite simple. And it turns out that such simple but optimal mechanism achieves an approximation ratio of 2/3. And just as a reminder, the previous state of the art was 1-1/E plus a small constant, even in the full prior information setting. So, but our new mechanism, despite using minimal information, already surpasses these previous results. Okay, so meanwhile, we also consider the setting that we only have sample access to the distribution. Prior to our result, there has been results showing that one sample is enough to achieve 1/2 approximation ratio. What's more, Kang, Pernis, and Wondruk further consider the symmetric case where the seller's distribution is identical to the buyer's distribution. They show that in this case, one sample is enough to get 3/4 approximation ratio. So in this paper, we consider the case where the designer has more than one but still finitely many samples. This is usually a technically more challenging regime. So we propose a new family of mechanisms using any finite number of samples called order statistic mechanisms and provide an exact characterization of the optimal mechanism for any number of samples in this family via a max-min optimization problem. So for the symmetric setting, so we solve the max-min program numerically and get these results, and we also give an asymptotic analysis. And also we also do something similar for the general setting, and our mechanism could almost achieve the previous state-of-the-art ratio as the number of samples grows to infinity. Okay, and these are all our results. And today, we will mainly focus on the left part, and in the remaining, I will try to explain the high-level ideas behind these results. Good. So let us start with the 4 prior information setting. So in this setting, the mechanism could see both the seller's and the buyer's distribution and also choose its price according to these distributions. So actually, we could see that in this setting, the optimal fixed price mechanism is quite clear and straightforward. Since the mechanism knows the distributions, it can simply calculate the expected welfare if we set the price to be P. Therefore, the optimal mechanism will always choose the price P that maximizes the expected welfare. Thus, like the approximation ratio on this instance for the optimal mechanism is just this term. And then the approximation ratio of the optimal fixed price mechanism is like just its ratio in the worst case instance. So it is the objective value of this min-max optimization problem. If we can solve this, we directly get the exact ratio of the optimal mechanism. But unfortunately, this optimization problem is really hard to solve because we need to examine all possible distributions, and this space is like an infinite dimensional space. Okay, so now let us get one step back and consider a suboptimal mechanism. This mechanism first fixes a set which consists of n numbers, namely we call them P1 to Pn. And then this mechanism chooses a price from Pi times the expectation of max S and B so that it maximizes the welfare. Or equivalently, we could think of this mechanism as it first scales the instance so that the optimal welfare is just 1, and then it chooses a price Pi so that it maximizes the social welfare. So these two ways are equivalent since scaling does not change the ratio. So similarly, we could see that the approximation ratio for this mechanism is this term. So it just takes the maximum over all possible n candidates. If we think of this mechanism as the second way, then we can first, so that is we first scale the instance so that the optimal welfare is 1, and then we can get an equivalent term for the approximation ratio. That is this one. So here we do not divide the optimal welfare because it's just 1, so definitely we don't need to divide it. So this term looks much nicer. So let us just consider this term in the following. Okay, now for this term, we could see that one thing good is that the inner maximization problem is kind of discretized optimization problem. Like since we only need to choose the best PI among all possible n candidates, so it looks much simpler compared to the former case that we need to choose like the optimal price from all real numbers. But this term like still looks hard to solve because like the outer minimization problem still requires us to examine all possible distributions, and we don't know how to solve them yet. So this suggests us to characterize the worst case distribution for this kind of minimization problems. Now let us consider a simple idea. For any distribution with a support on the interval like from A to B, we can always like spread the distribution to its boundary so that it is still a valid distribution with the same expectation. Like what's more, we know that distribution like this distribution after spreading is a 2-point discretized distribution. And we could apply such ideas in characterizing the the worst case distributions. So we could do something like similar operations to both the sellers and also the buyers' distributions and spread their distributions to the points pi minus epsilon and also pi plus epsilon, where epsilon here is a small enough constant that approaches 0. So like graphically, we are doing things like this. Like this is how we spread the seller's distribution, and we will also do something similar to the buyer's distribution. And it turns out that after this operation, the seller's and the buyer's distribution become a discretized distribution supported on like pi minus epsilon and also pi plus epsilon. More surprisingly, we could find that after such operations, the expected welfare decreases and the optimal welfare increases. So this implies that the approximation ratio of our suboptimal mechanism is worse after such operations. Therefore, such properties means that the worst case distributions for our suboptimal mechanism, which only like finds the best price among n candidates, is actually like a discretized distribution, whereas they only have probability mass on pi minus epsilon and also pi plus epsilon. So actually, like to be more accurate, we know that the seller will never put its probability mass on pi minus epsilon, and the buyer will never put like her probability mass on pi plus epsilon. So actually, like we know that it's so we know that the worst case instance is a discretized distribution like this. So now let us look back to our suboptimal fixed price mechanism. So we know that the worst case of the outer minimization problem must be achieved as some discretized distributions. So this is something that much nicer because like we change an infinite dimensional optimization problem to a finite dimensional one, and it becomes much solvable. So here we just set like n to be 16 and choose a specific set of parameters pi, and then we are able to solve this optimization problem numerically and get a lower bound of 0.72. So this is how we provide the lower bound for the full prior information setting. And in our paper, we also show that if we have enough candidates, then then this kind of suboptimal mechanism can be arbitrarily as good as the true optimal mechanism. Or like more formally, we have this lemma. So this lemma means that as long as we have enough computational resources, we can get some numerical results that is like arbitrarily close to the true optimal ratio. Good. But like till now, like maybe you will not be satisfied with this, like since in the last step we use a numerical program to provide the lower bound. Although we use a quite reliable optimization solver, which is Groby, to solve this program, you may still doubt that like, okay, maybe there's a hidden bug. Could we use such an idea to do anything theoretical? The answer is yes. So actually this idea like could help us to prove the theorem that the optimal approximation ratio knowing both the distributions is exactly the same as the optimal approximation ratio if only knowing one of them. Like for example, let us just consider the case like if we only have access to the distribution of the seller. So how do we prove this? Let us like first define R star to be the optimal approximation ratio in the full prior information setting. So as we discussed earlier, we know that it equals to this term. So this is what we have proved before. And our goal is to prove that the approximation ratio, only knowing the seller, is exactly the same as R star. But what is the optimal approximation ratio if we only know the distribution of the seller? So like given the distribution of the seller, the optimal mechanism is to find a distribution of prices so that it has the best performance against the worst buyer. So it's this term. And therefore, like similarly, we know that the approximation ratio is just like its ratio of the optimal mechanism in the worst case situation. So we just need to take the minimum over all possible sellers distributions, and we know that it is this term. And we could just like reformulate the term on the left to get this thing. So what we need to do is to prove this equation, and we know that this equation looks quite true intuitively, because like we are just exchanging the order of min and max here, so like this looks just like a simple application of min-max theorem. But however, we cannot directly get an equation here because of two reasons. Like the first one is that FB and delta P are infinite dimensional spaces. So like we cannot directly apply minimax theorem here because like we know that minimax theorem may be not true in the infinite dimensional space. And also the second reason is that the objective function may be not convex concave. So we can also like cannot directly apply minimax theorem. But the second one is easy to address. We only need to reformulate this term to a bilinear term like this, and it's easy to see that if this equation holds, then the approximation ratio for the one-sided setting is also R star. So what about the first one? So our previous lemma states that for any positive epsilon, there exists a suboptimal mechanism which is at most epsilon worse than the optimal mechanism. What's more, the worst case distribution for the suboptimal mechanism is a discretized distribution and thus is finite dimensional. So this means that we could consider discretized FB and delta P, which is in a finite dimensional space, and we only need to suffer a loss of at most epsilon. And then we could just apply the minimax theorem here because like the space is finite dimensional, and we get this equation. And finally, we could see that these two terms could be arbitrarily close, and just let epsilon approaches 0, we then finish our proof. And finally, due to time limitation, we are only able to give a proof sketch of our third result. we consider a case that we only know the mean and we provide the optimal mechanism and show that 2/3 is the optimal approximation ratio. How do we do that? So let us take the case that we only know the expectation of the seller as an example. Our first step is to show that the mechanism must be in this form. It first samples a number x from some previously defined distribution and then simply set x times the mean of the seller as the price. This is our first step. Our second step is to demonstrate that actually the worst case instance must be a 2-point distribution for the seller and a 1-point, or say like deterministic distribution for the buyer. Therefore, we only need to examine these instances to verify our claim, and this is like very easy to compute. Okay, that's all of my talk, and thanks for listening.